When we capture any astronomical image, of course, it's always important to get the exposure levels correct. In spectroscopy, if the exposure is too short or too long, absorption and emission features that we're looking for may not be visible or can be less visible. Let's take a look at this sample spectrum of Vega. It's a color image, and the profile over here looks pretty good. We can clearly see some of the hydrogen bomber features here, here, and here, for example. We might conclude that we did a really good job with our exposure levels. So let's look at the pixel map. There are as many rows in this grid as there are rows between the orange lines. As I move the orange lines closer together, you can see fewer rows show up on the grid. Okay, so now each cell in this grid is an intensity value of a corresponding pixel in your image that came from the sensor. As I scroll to the right, we can see the value of the pixels change too. And out here is a somewhat circular region. This is our star. Notice that quite a few of the pixels have a value of 255, which is the maximum pixel value for this bitmap image. Now, if this was a FITS file and you had enabled 32-bit processing on the options screen, the full-well maximum values would be a little more than 64,000. When we see values that are the maximum pixel value, like these 255s, that means we lost photons because the pixel well was full. Now that's totally okay with the zero order in our spectrum. RSpec can still find the middle of it when we're calibrating. But full wells are not okay in the profile data. So let's look at the same data in a 3D view. These values here are the rows in the image, and these values are the columns across the image in pixels. So let's see, it's about 1250 there, and over in the image we can see 1250 pixels. Okay, now let's closely examine the zero order. While I'm holding the control key down, I'll bracket in the star with my left mouse button down too. And now in the image we've zoomed in. Now we can clearly see that the star's pixels are all flat-topped because their pixel wells are filled or saturated. That means we lost data. But as I mentioned, that's okay on the star. Now let's look at just the spectrum. Holding the control and left mouse button down again, we can see the spectrum here. This is the same as our profile view. In fact, I can rotate it around and we can compare this to our profile and see the similarity. We can see here that none of the pixels seem to be higher than 255, the maximum well depth. So we could conclude again that our exposure levels are correct. But when we're working with images captured on a color camera, things are a bit more complicated. Now, just a quick comment about color cameras. You can do lots of great spectroscopy with a color camera. But for some of the more advanced scientific applications, a mono camera is more sensitive and can yield much better data. Okay, now just for a moment, let's review how a color camera works. In front of the sensor is what's called a Bayer filter or matrix. It's made up of tiny red and green and blue filters in front of each camera pixel. After you've captured an image, those colors are combined to display the entire range of colors. So to extract a spectrum from a color image, we need to know a single value, the monochrome intensity. Now, the only way to convert red, green, and blue pixel values to a single monochrome intensity is to average the color pixels. The average would be the red plus the green plus the blue divided by 3. In real-world use, we'd use a weighted average, but that doesn't affect our discussion here. So the intensity values we see in the 3D graph and in the profile are an average of the red, green, and blue values. So let's think about a typical pixel down here, say in the blue end of the spectrum. Maybe it's this particular pixel. There's very little red-green here because, well, this is the blue end of our spectrum, right? But maybe this particular shade of blue has a little bit of red and a little bit of green coming from our camera. So let's say that the red and green pixels in this area are, for the sake of our discussion, just 50 out of 255. But let's further suppose that we've overexposed this image so that the blue pixels are completely full, so they're 255. So red plus green plus blue is 50 plus 50 plus 255 or 355. And then to get the average, we divide by 3. So this pixel's mono intensity is 118. That's the value we see about here. But wait a minute, a moment ago we said that the blue pixel was saturated at 255. Why didn't we see the graph all the way up at the top and flat-topped here? We don't see a flat top because of the averaging. That 50 plus 50 plus 255 divided by 3 is just 118. So this averaging, which is unavoidable in order to get a single intensity value, is hiding the fact that we've overexposed our blue pixels. So how can we detect saturated pixels in color images? We can use this color channel feature in RSpec. Right now, the 3D graph is showing all the colors in that combined average. Let's look at just the blue channel by selecting this radio button. Wow, the blue channel is completely saturated. Look how flat top that is at the maximum pixel value. How about the green channel? Oh, wow, again, the green channel is saturated too. What about red? Well, that looks a little bit better, probably because our telescope optics and camera sensor are less sensitive in the red. So let's step back for a moment. What have we learned? We've learned that on color images, we can't rely on the simple pixel map of the composite mono image. Why? Because these are monochrome values, which is an average. The only way to know if our image is saturated, if it's a color image, is to look at each of the red, green, and blue channels to see if they're saturated. So when you're capturing spectra with a color camera, you need to pop up the screen and make sure you haven't saturated any of the 3 channels. And again, why do we care about saturated pixels? Because once a pixel well is full, additional photons are lost and don't contribute to the quality of the image. So what I've just shown you is, of course, just for color images. If you're capturing FITS images that are monochrome, this color panel won't be visible. In the next video tutorial, we'll show how this works in RSpec when capturing a video from a color video camera.